Assalamu alaikum everyone. Today we are going to study the next data structure, which is queues. We will also look at a special type of queue called priority queues. First we define what is queue. We look at examples of its application. Then we look at how to implement queue. Again, we're going to do this using two approaches, as we did with stacks, using an array and also using linked list. And then finally, we will look at briefly about priority queue. We shall not actually implement priority queue at this stage. We will do that later after we have learned a better data structure that can be used to implement a priority queue. Okay, so let's get started. What is a queue? A queue, like stack, is a linear data structure that grows by adding elements to one of its ends, which is called the rear, and shrinks by taking elements from the other end, which is called the front. Okay, so unlike stack, where only one side is allowed for both insertion and deletion, in queue both ends are allowed. However, one end is specifically dedicated for adding new elements, and that side is called the rear or the back, whereas the other side is used specifically for removing elements. Okay, that side is called the front. Okay, this figure shows the nature of a queue. So both sides are open, but one side is used for adding, which is called enqueuing, and the other side is dedicated for removal. Okay, this is the front of the queue. Okay, as we shall see, again, there's a name for removing an element in a queue. It is called dequeue. Okay, so this is the idea. Queue is therefore exhibiting what is called FIFO structure. FIFO means first in, first out. Okay, as you can see, the first guy to come in will be the first guy to go out. Okay, and therefore a queue is called FIFO structure. There are, of course, many real-life examples of a queue. We will talk about a few of them in the coming slide, but this diagram is showing you an example. If you go to an ATM machine, you may likely find people in a queue trying to access the ATM machine. So this is a natural example of a queue. Anybody coming will queue behind this guy at the back, and when this guy finishes, he will get out of the queue, and the next one following him will be in the front of the queue. This is the idea of a queue. The following operations are needed to properly manage a queue. We have enqueue, as I mentioned in the last slide. Enqueue an element. This means putting an element at the end of the queue or at the rear of the queue. Okay. The other operation is dequeue. Okay, so dequeue, this is very specific. It simply means delete the first element, the element at the front of the queue. Okay. Then we have first element. This returns the element at the front, but without removing it. So very similar to dequeue, because dequeue also is not void. It's going to return the element that has been removed, the one from the front, remove and return it. But here, just return it without removing. Okay, we just want to know who is at the front of the queue. So these are the three important methods. You can see they are very similar to the method of stack, where we have push, pop, and top element. So here we have enqueue, dequeue, and first element. Of course, we normally also have clear to empty the queue. Is empty to check if the queue is empty. You may have toStrings and other commonly used methods. This figure demonstrates how a queue works. So we start with an empty queue. If you enqueue 10, it will be at the front of the queue. It will be the only element. Okay, so it is both the one at the front and also the one at the end. But if you enqueue 5, it will come behind the 10. So now 10 is the one in the front and 5 is the one at the rear. If you now call dequeue simply means remove the front element. Okay, so 10 will be removed and you will be left with 5. In queue 15 will go behind 5. So it is the last element or the element at the rear. Okay, and 5 is now the front element. In Q7, it will go behind the 15. So 7 is now the last element. All right. Finally, if you call dequeue, it will dequeue the front element, which is 5, and you will be left with 15 and 7, and so on and so forth. So this is how a queue operates. Let's talk briefly about some of the natural examples of applications of queue. So wherever waiting lines are required to access a service or to use a common resource, queue will normally be required. So queues are commonly used in systems where a waiting line has to be maintained for obtaining access to a resource. Some examples are ticketing systems at the banks, sales offices, and so on. Okay, so in each of these situations, usually when you go there to obtain a service, you will obtain, there will be a machine where you will click to obtain a ticket. Your number will automatically be put in a queue. Okay, and so we normally see this, of course, in the banks or sales offices. Like if you go to any of these telecom sales offices like STC or Zain, you will see that they have a ticketing system. Just click the machine, it will give you a number, and that number will be placed in a queue. So the people handling the sales will be following the queue. They will remove one number from the queue and service it, and the next number will be moved forward, okay, and so on. This is basically a very common example. Another example in programming is in operating systems, okay, in multi-programming situation, or what is called multitasking. So here, as we know, most computers, they have only one CPU, but you will see that many programs are running seemingly as if they are running in parallel. Okay, so within your computer or even your phone, you may open many different apps at the same time, but actually only one of these apps can access the CPU at a time, and therefore the operating systems needs to keep a queue to track how to allow these different apps to access the CPU. Okay, So it will take one up from the queue, allow it to access the CPU. Very briefly, you will not even notice that it is the only one that is accessing the CPU, and then allow the next application, and so on. Okay, so this is the idea of multi-programming or multitasking system. Normally, it is implemented using a queue. Another common example is in network printers. Okay, so you have a printer attached to the network. Many users are sending their print jobs. There has to be a way to organize these jobs, otherwise there will be chaos. You may have one page of this job printed, then another page, and so on. Now what will happen is the printer maintains what is called a print queue. So when a job comes, that job is automatically enqueued in the print queue. Okay, if another comes, it will also be enqueued in the queue, and so on. So the printer will be removing a job from the print queue, print it, and then remove it from the queue. Okay, and then it will go to the next one, and so on. So this is a very common application of a queue. Another example is with network servers, be it a web server or mail server or any other server on the network that provides some service to its clients, usually has to maintain a queue. So you can imagine, for example, a web server. Many users are trying to access documents from that web server. Most likely, there will be more than one user trying to access a page at a time. So if there is no queue, there could be a problem. So what will happen is, as requests come to the server, they will be enqueued in a queue, and the web server will simply be removing a request from the queue, service it, and then get the next request, service it, and so on. This is the way the servers normally they organize their job. Otherwise, there will be chaos. Similarly, with the mail servers, when users of a mail service they sent an email, the mail server is the one that will handle the process of forwarding this mail to its destination. So again, there may be many mails coming from many users. So to maintain order, a queue is used to store these mails, and then the mail server will be taking them one by one from the queue and forwarding them to their destinations. There are many applications of queues. This is just an example or a set of examples. Let us now look at implementation of queue. As we did with stack, we're going to look at two approaches, using array and also using linked list. Okay, so we're going to start with the array implementation. It says here one possible queue implementation is using an array. However, with array, there is a problem that needs to be sorted out for it to work efficiently. To demonstrate this problem, let us suppose that you want to use an array of size 10 to implement a queue of integers. Okay, so we use an array of size 10 to implement a queue of integers. Let us say after enqueuing 7 elements in your array, the queue looks as this. Okay, so we have these 7 elements in the queue. Obviously 3 is in the front and 2 is at the rear of the queue. Alright, now suppose you dequeue 2 front elements. The 2 front elements are 3 and 7. So suppose you dequeue 3 and then you dequeue 7. Okay, you may have a situation like this. These are the remaining elements. Okay, the question is what will be the positions of these remaining 5 elements? Okay, a natural way to think about it is the way we handle queues in real life. So when 3 is deleted, 7 will automatically shift to replace its position, and the rest of the element will also shift forward. Again, when 7 is deleted, the elements are all shifted forward by 1 space. This is how we do in natural life. In a human queue, this is what we do. But is this efficient in a programming situation? Okay, obviously not. Shifting elements forward each time an element is dequeued is definitely not efficient. Just because you remove one element, okay, assuming you have a queue of 1,000 elements or maybe 1 million, then you have to shift each of these remaining elements, about 1 million of them, by one. This is definitely not efficient. Okay, so while it may be efficient in human sense, in programming sense, it's not efficient to shift elements just because one element is deleted. Okay, so if we don't delete, then we're going to have another problem, because it means we can only utilize the remaining cells at the end of the queue, and very soon they may be exhausted. Okay, so this is what the second point here is saying. Keeping them where they were, that is the remaining elements, if you keep them as they are here, and then enqueuing only at the rear, so utilizing only the remaining cells, it means the empty slots that are left by the deleted elements will never be used again, and very soon these ones will be exhausted and you have a problem. So this option is also not good either. The question is there a more efficient way of handling this situation where we don't have to shift the elements, but also we will still utilize the remaining cells, the cells that are left by the deleted elements? Is there a way to do that? And the answer, of course, is yes, there is. It said to solve this problem, the array is going to be treated as if it is circular, as shown in this figure. Okay, so although we know array is linear, we think of it like it is circular. What that means is when you reach the last element, you're going to insert the next element at the beginning. Okay, so if in that way the array is treated like it is circular, so the last cell is assumed to be followed by cell number 0, and so on. So even though you are adding only at the end of the list, actually you will come back and use those cells that were left by the elements that were deleted. This is the idea. So if you think of it like this, you need to maintain 2 references, first and last. First will be pointing to the first element, so it's like the index of the first element in the queue, and last will be the index of the last element, the element that was enqueued last. We need to use these 2 references, first and last, to keep track of the index of the first and last element respectively. Let's take an example of enqueue situation. Okay, last could be at the end of the array, or it could be somewhere before the end. So you need to be able to handle the 2 situations accordingly. So here it says if last is at the end of the array, then the next call to enqueue will enqueue at position 0. So as you can see here in figure D, last is 8. So the next element that we're going to enqueue, we're going to cycle back and enqueue it at position 0. So at the beginning of the array. Okay, so this is the idea. The other situation is say else enqueue at the next empty cell. So this is the normal typical situation. There are still more cells before the end of the array, yani after last. So if another element comes, just update last by 1 and put it in that next position. Okay, so this is how we will be treating enqueue. Now dequeue is done similarly. It's not shown in this figure, but you can imagine it. Of course, to dequeue means remove the element at the front. Okay, so again there are two situations. If first, remember first is pointing to the first element, so it's the one we're going to remove. So if first is at the end of the list, after removing that element, the next first is going to be at position 0. So that's what we are saying here. If first is at the end, next first will be at index 0. But if first is not at the end of the array, then after dequeuing this element, the next first is going to be just the next cell after the current one. Okay, so this will be the next first. This is the idea. So when we are implementing enqueue and dequeue method, we need to take care of this situation. Okay, so this will solve the problem of having to shift the elements after each dequeue. Okay, no need to shift. Just think of the queue as circular. When you reach the end, just come back to position 0. However, for this to work, we need to be careful that the queue could be full. Okay, so this is what this point is about. It says since array can be full, this implementation strategy must be able to detect when the queue is full. Okay, and with the array being treated as circular, there are two possible conditions for the array to be full, as shown in these diagrams A and B. Okay, the first case is the first variable could be pointing to position 0, and the last variable will be pointing to the last cell in the array, so the one at length -1. If this happened to be the case, so basically after inserting, we keep inserting, we never dequeued until the array becomes full. So this is one condition for the array to be full. Okay, but a more typical situation is like this, because normally you will be enqueuing and dequeuing randomly. So if you are doing that, most likely first is not going to remain at position 0. First may be somewhere in the middle. Okay, so if that is the case, the condition for the queue to be full is if last has reached the end and has come round, and it is now just before the first. So if last is just before the first, then again this is another condition for full, because now we cannot move, we cannot insert another element. If you try to move last by 1 position, you will be replacing this element, which is not right. Okay, so this is the second case. The second case is first is right after the last. As you can see, first is immediately after last. If that is the case, then again this is another condition for a full queue. So these cases we have to take care of when we come to the implementation. Now with this strategy, let us try to come up with a class that will implement a queue using array. Okay, Remember the idea, we're going to use two reference variables. They are going to be integer variables because they will be index or indexes of the first element and the last element. Okay, so this is our implementation. It's called array Q. As we said, we need int variables first and last, to refer to the first element or to keep track of the first element in the queue and the last element in the queue. We're going to also need size. We will see what it is used in a moment. And of course, this is array implementation, so we need an array to store the elements. We have chosen to use array of objects. As you remember, object is the superclass of all classes. So if you have an array of objects, you can store any type of data inside. You can store integers, doubles, students, items, and so on. So we're going to use an array of objects to store the items. Perhaps a better way to do it is to use a generic type T, but unfortunately Java doesn't allow array of generic type to be created. So we will have to use array of objects. Okay. What about the constructors? We have two constructors. The first one, we are allowing the user to specify the size of the queue. So he will provide n, and that n, as you can see, we are using it to initialize size. So actually size is the capacity of our queue. How many elements can our queue hold? It's not the number of elements in the queue, just the capacity. Okay. Right, now once you have n, this array, we can now go and create it. You can see at the moment it has not been created, but the constructor is creating it. It's saying storage equal to new array of object of the given size. So the array has been created. What about our tracking variables, first and last? They are being initialized by the constructor to -1. Obviously, we all know that the index of the array starts from 0 and it will never be negative. So we need a special value for this variable to indicate that the queue is empty. So to do that, we'll initialize both first and last to -1. Okay, so -1 means so far there are no elements in the queue. The queue is empty. Okay, so this is the main constructor. What if the user doesn't provide any size? Or we can create an array of size 100 in that case for the user as the default size. Okay, so this is what this constructor is doing. As you can see, it's calling the other constructor but sending 100 to be the value of n. So an array of size 100 is going to be used to create this array. I mean to be used for the queue. Okay, good. Now let's talk about the enqueue and dequeue methods. Enqueue normally will affect a lot because we always enqueue at the last. But actually there are three scenarios that we have to worry about. First, the queue could be empty. So in that case, not only do we have to worry about last, but we also have to worry about first, because when we put the element, normally we will increment last by 1 and put the new element there. But because this is the first element, we cannot leave first to be empty. I mean, we cannot leave it as -1, so we also have to update it in that case. So one scenario is if the queue is empty. Another scenario is if last is at the end of the array. Okay, so the next element is going to be at position 0. And then the final case is the typical one where last is somewhere in the middle, so the next element will be put just in the next cells. So those are the three cases that this enqueue method is trying to solve. Okay, let's go through it. it receives an element to be enqueued. So first it checks, is last equal to -1? Meaning, is the queue empty? If it is empty, this is the first element we are receiving, therefore we're going to store it in position 0. So we say storage at 0 becomes element. Okay. After that, we need to set both first and last to 0, because now we have an element, one element, and both first and last should be pointing to it. So they are set to the index of that element, which is 0. Okay. Else if last is equal to size -1. So we are saying in case the last variable is at the end of the array, then we know we should store this new element in position 0, because the array is circular. Remember, when we reach the end, we have to come back to 0. Therefore, storage at 0 becomes element. In other words, store the element at position 0. Of course, you have to update last to be 0, because last is always the index of the last element. Well, this is the element we have just enqueued. We enqueued it at position 0, therefore last is equal to 0. Okay, the final case is the typical one, the most common one, where last is not at the end of the array. So in that case, we just need to increment last by 1 and then put our new element at the new position of last. Now you can do this in 2 statements if you wish. So you can first increment last, you can say last plus plus or plus plus last, and then storage at last becomes element. But here I'm combining the 2 statements into one. So I say storage at plus plus last equal to element. Now here you have to be careful. You cannot say storage at last plus plus, because if you do that, the element is going to be stored at the current position of last. After that, last will be incremented by 1. That is not what we want. What we want is first move last by 1 before you do this assignment. So if you want that, you have to make this to be plus plus last. Okay, so storage at plus plus last becomes element, meaning move last by 1, then store the new element at the new position. So this is the enqueue. What about dequeue? So again, dequeue, there are 3 possibilities, just like enqueue. We could have a situation where there is only one element in the queue. So if we delete it, not only should we update first, because normally the queue involves updating first, but if this is the only element you are deleting, then not only do you have to update first, but you also have to update last. Okay, the other 2 cases are similar to the one for enqueue. We could have a situation where first is at the end of the list. So if we dequeue that element, the next first is going to be 0. We're going to cycle the first back to 0. Okay, and the last case is the typical case where first is in the middle of the array. So after you remove the current element being pointed by first, just update first to be the next cell. Okay, this is what we're going to see in this method. Okay, so the first thing, because this method is not void unlike enqueue, we're going to return the element that we are dequeuing, or that we are removing from the queue. So what is that element? Obviously it is the one pointed by first. So you have to say storage at first, save it into a temporary variable of type object temp. So save the element, we will return it at the end. But before that, we have to delete it from the queue. Good. Okay. Obviously we cannot say return at this point because that will end the method. So save the variable, and then do the deletion, and then return 10. Okay, now let's look at the three cases. The first case is if first is equal to last. What this means is there is only one element in the queue. So to delete it, all we have to do is empty the queue. And to empty the queue, we just need to set the two variables first and last to be -1. Second case is if first, if it is at the end of the array. So how do we know that? By comparing first with size -1. If first is size -1, it means first is at the end of the array. And therefore the new value of first is gonna be position 0. Okay? Otherwise, we just need to increment first by 1. Okay? Now notice that this dequeue actually doesn't really delete the elements in the array, because really you cannot delete an element in an array. You can only ignore it. Okay? So by moving first to the next cell, we are basically ignoring the tree. Okay, so we are saying our next first element is here. Okay, so this element can never really be deleted. You can set it to 0 if you wish, but it doesn't mean anything. The value is still there anyway. Okay, so unlike linked lists where you can really delete values, in an array you cannot delete, you can only ignore. So just by moving first to the next cell, it means 6 is our new first. We're going to ignore this 3 there. All right, so this is the idea of the queue. Let us see the remaining methods. First element, if you remember, it should return the element at the front but without deleting it. So to do that, just say return storage at first. Okay, is full. Remember, there are two conditions for is full. So this method has to check both and return true accordingly. The first condition is that first is 0 and last is size -1. Okay, so last is at the end of the array. This is one possibility for the queue to be full. The second condition is last is just behind first. So if you add 1 to last, it will reach first. If this is the case, this is another possibility for the queue to be full. Okay, so we are saying either of this, return true. If any of these two conditions is true, return true. The queue is full. It's empty, of course, if first is -1. If you wish, you can say if last is -1, because when the queue is empty, both of them are equal to -1. Clear, just set both variables back to -1. And the last method is print all. Now this is very interesting. If you remember the print all for stack, we just call the toString for the array list. But here we have to be careful. We cannot just print the elements of the array from 0 to the end. Okay, if we do that, they may not be in the order of the queue. We always want the first element to appear first when we print. And as we remember, there are two possibilities. We could have a typical situation like this. Okay, so to print the queue in this case, just start from first until last. This is what this if statement is doing. It's saying if first is less than or equal to last, as in this case, first is definitely less than last. So in that case, you just need a simple loop for I from first. So we start from first. As long as I is less than or equal to last, I plus plus. What do you do for each I? Print storage at I. So it will print 2, print 4, print 8, print 6, and so on. Okay, so for this scenario, this loop is good. But we have a scenario like this, where last has reached the end and has cycled back. Okay, so in this case, this condition is not true. first is not less than or equal to last. You can see here first is greater. Okay, last is now 0. If you add one more element, it will be 1, and so on. So in all cases, in this case, first is going to be greater. So how can we print the elements in this case? In the order from first to last. Okay, to do that, actually you need 2 loops. First, you need a loop from first to the end of the array, and then from 0 until last. Okay, last happened to be 0 in this case, but it could be anywhere before first. So we need a loop also from 0 until last. Okay, so these are the 2 loops that will do that. So in case this condition is not true, first we print for I from first until the end of the array, so until size minus 1. You should notice we are using less than here. Less than size means until size minus 1. Okay, what do we do? Print the element at I. After that, do another loop from 0 until last. So from 0, as long as I is less than or equal to last, print the element at I. So this will again print the element 2, 4, 8, 6, just like the other one. So this is how to print all, and this is the implementation of a queue using an array. Let us look at a more simpler and more natural implementation using doubly linked list. Okay, so we're going to use the Java's linked list, so we are importing it. And our class here is called LLQ, linked list queue. It is really generic. It doesn't need to use the object class. It is using generic type T. So like we did with stack, we're going to create an object of linked list. Okay, our constructor doesn't have to do anything. We have already created the linked list object. So we're basically going to utilize the methods of linked list to implement the method of queue. Okay, so this is the first method, enqueue. Remember, enqueue, we enqueue at the end of the list, and the natural method to use therefore, just like stack, is add. So we say list.add element. So a new element will be added at the end of the list. Okay, as simple as that. What about dequeue? Now dequeue, remember, we need to remove the element at the front. The question is, which method of linked list will allow you to remove at the beginning? Well, we have remove first, so this is the method to use. Okay, so it says return list.remove first. Okay, so remove first will actually remove the first element in the list and return it. Okay, the method is not void, so you have to return the value. Okay, what about first element? Again, linked list has a method get first, so it is the method we should call to get this value at the beginning of the list without removing it. As you can see here, list.getFirst. Okay, return list.getFirst. So those are very easy implementation of the 3 principal methods of a queue. Other methods are straightforward. Clear. To clear the queue, just clear the list. The queue is empty if the list is empty. And toString, just call the toString of the linked list. It will return the elements in the list in the order they are here from beginning to end. Okay, now this is more natural way of implementing it, but actually there is nothing preventing you from making this side to be the front and this side to be the rear, as shown by this diagram. Okay, so it's up to you. This is more natural, but if you wish, you can implement it this way as well. just you have to call the appropriate method. Okay, so for example here, if you are following this idea, then to enqueue you cannot call add, because add will add at the end. In that case, you have to add. There is a method add first, so this is the one you should call. Add first, or if you like, add at 0. There's another one that takes an index, so you can give it 0. It will add at the beginning of the list. Okay. What about dequeue? To dequeue, this is the one we want to remove, so you cannot say remove first. In that case, you have to say remove last. Okay, because we want to remove the element at the end of the queue. All right. What about get first? First element. To get the first element, this is now the first element, not 9. So we have to call get last. Okay, and so on and so forth. So it is possible actually to implement a queue, not necessarily by calling this method. You can think of the queue this way, and you will call the right method to do it. Notice, however, that in that case, your toString is not correct, because it is printing the elements from last to first. So you have to find a way of printing the elements in reverse. Okay, good. So this is the implementation of queue using linked list, and the comparison between the two implementation is very similar to what we already discussed with stack implementation. Okay, there's nothing new to add. Basically, with array implementation, you may be wasting memory, or you may be wasting time if you have to create a bigger array to copy the numbers or the elements to the bigger array. Whereas with the queue implementation, you never need to create a node that is going to be wasted. We only have the nodes that are needed to store the elements. If you dequeue an element, the node for that element is deleted automatically, so there is no wastage at all. Okay. So the linked list implementation is much more efficient and actually much more easier to implement, as we saw. The last subtopic to discuss is priority queue. As I mentioned, this is going to be just a brief introduction because we're not going to implement it yet until later in the course. So in many situations, simple queues are inadequate, as when first in, first served scheduling has to be overruled using some priority criteria. These are examples. Emergency cases in hospitals. You can imagine an accident happen and you have some patient in critical condition. It doesn't make sense to say put them in the queue. No, you take them directly to the emergency ward so that they will be treated. So in that case, the normal queue has to be overruled and treat the most emergency situation first. Handicapped persons in a post office or in some sales place or even in a college, normally you give them priority. Okay. Police cars, ambulances, fire engines on the roads, again, we normally give them priority because they have more urgent situation to handle. Okay. In programming situation, you may have a sequence of processes, but where some processes must be executed before the others for the proper functioning of the system. Okay, there are cases which we call producer-consumer relationships. So one process has to generate some data before another process will use that data to do further processing. So in that case, you have to give those that will produce the data more priority, okay, than those that will use the data. So there are many real-life situations where you will have to override the normal queue situation. Okay, so the question is, how do we handle this? Okay, first a definition. A priority queue is a queue that allows elements to be dequeued according to their priority and according to their current position in the queue. Yeah, so it's important to take note of the second point as well. You may have two elements with the same priority. So how do you manage them? Basically, now you have to look at who among them came first. Okay, so priority queue is looking at both priority as well as the current position in the queue. All right, and notice the emphasis is on dequeuing because we want to process the highest priority element first. It is the dequeue method that actually handles the processing. Okay, so priority queue is a queue that allows element to be processed, if you like, or to be dequeued according to their priority and their current position in the queue. Now there are two main approaches that are used to implement priority queue. One is called ordered list. In ordered list, each new element is enqueued according to its priority. So when a new element comes, you don't just put it at the end as we normally do in normal queue. No, you're going to search the current list of elements, find the correct position to put this new element based on its priority. So you can see that in this way, the elements in the list are always ordered according to their priority. Okay, when a new element comes, you don't just put it at the end. Find its correct place based on its priority and put it. So the list remain ordered by priority. Okay. However, the dequeue process doesn't change. Okay, it remains as before. Simply dequeue the front element. Okay, so we only need to change the enqueue method. The enqueue will not just enqueue at the end, at the rear. No, it will enqueue based on the priority of the new element. But the dequeue method remains as before. So this is one approach. The other approach is the opposite. We call it unordered list. So what does this mean? Elements are queued at the rear as before. So when a new element comes, you don't have to find its correct place. Just put it at the end. In other words, don't make any change to the enqueue method. However, in this case, the dequeue operation requires searching to find the highest priority element. So when you want to dequeue, you have to now go through the whole list, find the highest priority element, dequeue it, and process it. Okay, so in this way, you see the elements in the list are not ordered by priority. That's why it is called unordered list. So these are two ways to handle priority queue. Either you change the enqueue or you change the dequeue method. However, although linked list can be used to implement priority queue, okay, such implementation will be inefficient. Can you think of the reason why? Well, simply because linked list only allows linear search. Because you see, in either of these approaches, we have to search. In the first case, we have to search the list to find the correct place to enqueue the element. Well, linked list allows only linear search. You have to start from the beginning of the list and be going one by one. So if there are 1 million elements, you may have to do 1 million search before you find the correct place to insert your new element. Similarly here, the searching is in the dequeue. Okay, the elements are randomly arranged. So to find the highest priority, you have to search. And again, searching in linked list is linear search, which is very inefficient. So for this reason, we're not going to implement priority queue at the moment. We're going to delay it until later in the course after we have learned a very efficient data structure that allow us to achieve priority queue without having to do linear search. And that data structure will be binary heaps, as we shall see later. Okay, so this is the end of this lecture. Thank you very much.